Up until now, we have only considered fluids that are static, or really do not go anywhere. They don't flow. By their very nature, fluid does, well, flow. So here we want to look at some of the properties of flowing fluids. When we talk about a fluid moving, we need to consider the volume of the fluid moving. Think about a garden hose and the water that is flowing through it. At any given time, there is a certain volume of water in the hose, or any section of the hose. This volume can, of course, be found by taking the area of the hose and multiplying it by the length of the hose. The flow rate of the hose depends on how much time it takes for that volume of water to flow through the hose. So how many cubic meters does the heart pump in a 75-year lifetime if the average flow rate is 5 liters per minute? Now the units for flow rate can vary depending on what unit of volume and time you choose. In this case, it is liters per minute. Our time is given in years, so we do need to figure out how many minutes there are in 75 years. Since there are 5.26 times 10 to the 5th minutes in 1 year, taking that times 75 gives us 3.945 times 10 to the 7th minutes in a 75-year lifespan. It doesn't really seem like very many, does it? We can rearrange our flow rate equation to solve for the volume of blood by multiplying the flow rate of 5 liters per minute by the minutes in 75 years to find 1.9725 times 10 to the 8th liters. But of course we want to find the volume in cubic meters, not liters, so we need to convert, and we find 2 times 10 to the 5th cubic meters of blood. As a reference point, this equates to about 200,000 tons of blood, or enough to fill 200 6-lane 50-meter pools. We can actually derive that relationship by looking at our flow rate equation. The volume of a cylinder is the cross-sectional area times the length of the cylinder. If we divided both sides by time, we get the expression for flow rate on the left as the area times distance divided by time on the right. And as we know, distance divided by time is the velocity. So now we can talk about flow rate in terms of velocity of a fluid moving. These two things are related but also depend on the area of the container. The Amazon River moves at a considerably slower velocity than a mountain river, but holds much, much more water than the mountain river. So even though the river rapids have water moving at a high rate of speed, the volume difference actually works out that the Amazon has a higher flow rate. Flow rate can be found by multiplying the cross-sectional area by the velocity. We can look at this equation and see that the flow rate is directly proportional to both the size of the container and the speed at which the fluid is moving. So what happens if the cross-sectional area changes through the container? Say we have a container that initially has some area, A, and the fluid is moving at some velocity, V1. At some point, the container changes its shape into a smaller area, A2. You probably have some idea that the velocity of the fluid is going to have to increase in order to keep the same flow rate. Take a garden hose that has some flow rate. What happens when you close part of the nozzle with your finger? The flow rate stays constant because the fluid is incompressible and there are no leaks in the system. So the same amount of fluid must flow past any given point in the tube in the same amount of time. But in order for that to happen, the velocity of the water must increase. So the flow rate through area 1 is equal to the flow rate through area 2. We also know that the flow rate is equal to the area times velocity. If the flow rate stays constant, we can say that the first area times the initial velocity is equal to the second area times the second velocity. We can also look at this in terms of the volume of fluid flowing through the tube. This shaded area represents some volume of fluid that is moving through the first section of the cylinder. As the tube narrows, the length of the volume must increase. And so again, in order for that same volume of fluid to travel past any given point at the same rate, the velocity must increase. Suppose we have a nozzle with a radius of 0.250 centimeters and it's attached to a garden hose with a radius of 0.900 centimeters. The flow rate through the hose and nozzle is 0.500 liters per second. Calculate the speed of the water in the hose and the nozzle. We want to know the velocities in each section and we are given the flow rate. So our flow rate equation is a really good place to start. Before we do anything, let's convert our flow rate from liters per second to cubic meters per second so all of our units match up. The velocity is determined by the flow rate divided by the area. And since our fluid is in the shape of a cylinder, we can use our pi r squared to determine the area, giving us a velocity of 1.96 meters per second. And this is for the hose. This is for the hose part. For the velocity through the nozzle, we can do the same thing, and we find a velocity of 25.5 meters per second. We could also use our change in area to determine the velocity through the hose. If we solve for the second velocity and plug in our numbers, we still get a velocity of 25.5 meters per second for the water in the hose. What is interesting to note here is that the velocity is proportional to the square of the radius of the tube. So a small change in radius can have a very large effect on the velocity of the fluid. One interesting thing to note about the relationship between area and velocity is that if you happen to have more than one branch flowing into or out of your system, the sum of the flow rates in each branch maintain a continuity of flow. So our equation can be written to account for more than one branch flowing through the system. In this case, N1 is the number of branches on one side, and N2 is the number of branches on the other side. So calculate the average speed of the blood in the aorta if the flow rate is 5 liters per minute. The aorta has a radius of 10 millimeters. Pretty straightforward in that we want to find the velocity of the blood. Again, we want to convert our flow rate to cubic meters per minute and our radius to meters. We can also go ahead and convert that cubic meters per minute to cubic meters per second. And from here, it is a simple matter of plugging in our knowns and finding 0.27 meters per second. So if the rate of the blood flow into the aorta is 5 liters per minute, the speed of the blood in the capillaries is about 0.33 millimeters per second. Given that the average diameter of a capillary is 8 micrometers, calculate the number of capillaries in the circulatory system. Well, we are comparing the blood flow from one large vessel into lots of smaller vessels. We can assign the aorta the one side of our equation, and there's only one aorta, so n equals 1. The radius was given beforehand as 10 millimeters, which we converted into meters, and we found the velocity as 0.27 meters per second a couple of minutes ago. The radius of a capillary is significantly smaller than at 8 micrometer. Micro means 1/millionth, so we can write that as 8 times 10 to the negative 6 meters. And the velocity of blood through the capillaries is 0.33 millimeters per second. This can be written as 0.33 times 10 to the negative 3rd meters per second. Alright, so we can convert all of that into the meters pretty simply. And if we plug all of those in, we end up with 5 times 10 to the 9th as our number of capillaries in the body. Notice how much slower blood moves through the capillaries than it does through the aorta. This makes sense if you think about why you have capillaries in the first place, which is to allow gas exchanges in the blood. So you think that number is reasonable? 5 billion capillaries in your body? Kind of cool.